I hope you can hear me okay. So, and happy Monday to everybody. So hopefully everybody saw my message about the first test. Just a reminder to make sure you send your emails about any test one adjustments to my Canvas email, not my regular email. And please be patient. I'm going to do them all at once in one batch next week during reading break. Okay. So once you've sent your message in, don't worry, I've got it. I will do all the changes, the adjustments. Okay. And I'm just looking at whether your answer was right on your CrowdMark sheet, but it didn't show up in the Canvas. Okay. Or you had some different number in the Canvas for some reason. Okay, that's what I will be checking, and also, of course, rounding errors and the few people who sent me documentation about connectivity issues. All right. So, are there any questions about anything before we get started this morning? Okay, I don't see any questions, so we're going to try and get started here. Okay, so we're going to do some more of Chapter 6 today, and we'll do a bunch of Chapter 6 stuff on Wednesday as well, and start Chapter 7 on Friday this week. So as you know, Chapter 6 is all about work and energy, and so today we're going to look at the connection between work and potential energy, and also look at total mechanical energy. So today we have a bunch of clicker questions, poll questions, and not so many examples. And then on Wednesday this week, we'll do more example problems once we understand all of the concepts. So today we're really concentrating on these energy concepts. And energy seems like a simple concept, but there are some subtleties there. So I wanted to make sure that we had everything completely clear in terms of all of those conceptual ideas before we do a bunch of problems here. So yes, Chapter 6 is the cutoff for our next test. Okay, so this is this comic actually relates to a demo I like to do, and I have a nice video of this demo, which is a really nice illustration of conservation of mechanical energy, which I'll show you on Wednesday. But I can tell you that right now they're not doing the demo correctly, because you definitely don't want to start with the bowling ball high up and swing it towards your face. That's not the way to do this demo. Okay, so one concept we need to talk about in the context of energy is are what are known as conservative forces. So a force whose work depends only on the endpoints of the motion is called a conservative force. So that's the definition. Okay, it's defined in terms of the work. So we have run into a couple of conservative forces. We talked about one of them on Friday, and that was the gravitational force. And we saw that the work done by a gravitational force only depends on your initial vertical position and your final vertical position. It doesn't matter which way you went. Okay? So for example, if you start at position Y1, one thing that's important for this formula is that it does require positive Y to be upwards. Okay, so now that we're doing energy here, we do need positive Y to be upwards. So we start at position Y1, we end up at position, Y initial, we end up at position Y final. Okay, and we know that that if we're on the surface of the Earth, right, that there's a gravitational force acting on our object as it moves. And so we can look at the work done by gravity, and we have an upwards displacement, and we have a downwards force here. Okay, so you can see, for example, when an object rises, Okay, when y final is greater than y initial, you can see if you plug those numbers into the formula there, you get a negative number. Okay, and then if you look at what happens in terms of the displacement here and the force due to gravity, you can see that they point in opposite directions. And we know that if the displacement and the force point in opposite directions, you should get, the work should be negative. The work done by that force for that displacement should be negative. And then similarly, we can look at what happens if the object falls. So if the object falls, then that means that the initial y is bigger than the final y. You started off higher up, right? And in that case, then your displacement would be downwards and your force would be downwards. They would both point in the same direction and you would get positive work. So gravity does positive work when something falls. It does negative work when something rises. And that's always good to keep in your mind when you're looking at the work done by gravity. So that's one conservative force. The other conservative force that we're going to look at this semester is the spring force. And this showed up in the pre-lecture a couple of times. So how do you calculate the work due to the spring force? So the idea is, here's one of the pictures from your pre-lecture. So in the case of a spring, what you're looking at is how far is the end of the spring away from the equilibrium position where x is equal to 0. So you have an x-axis. You say when the spring is neither compressed nor stretched, that's your equilibrium position. That's x equals 0. Okay, and at that point, there's no spring force. But as you begin to stretch a spring, the spring wants the end of the spring, it wants to go back to its unstretched position. So there will be a force pointing back towards the origin, back to x equals 0. Okay, and so you can see here you have the displacement and the spring force point in opposite directions. Okay, so the spring force is going to be doing negative work there. And similarly, if you compress a spring, right, then the spring wants to go back to its original position. So if you compress, right, your displacement will be in the negative direction, but your force will be in the positive direction. And again, you're going to get negative work done by your spring. And how much work depends on the sizes of x2 and x1. Okay, so that's another conservative force, and it only depends, again, on the initial stretch of the spring, x1, and the final stretch of the spring, x2. It doesn't depend on how many times you went back and forth. So the spring could go back and forth many, many times in between, okay, and it wouldn't matter. All matters is where it started and where it ended up. So I thought we would do a quick spring question. Since we haven't done springs, this is the first time we've looked at springs in here. I thought we would do a quick poll question. This one's only got 3 choices. Okay, so there are 3 choices. And so what do we have? We say we have a box and it's at rest and it's attached to a spring at its equilibrium length, so neither compressed nor stretched. And now you push the box with your hand so that the spring is compressed a distance d, big D, and you hold the box at rest in this new location. So you imagine pushing it and holding it. During this motion, the spring force does negative work, 0 work, or positive work. So you can either look at the formula here for the work done by the spring force, or you can look at the directions of the spring force and the displacement and think about how the directions of those vectors affect the sign of the work. Okay, I think we'll do 10 more seconds here. So go ahead and guess if you're not sure. Okay, 5, 4, 3, 2, 1. Let's see what everybody thought. All right, what do we get? So we've got the biggest group think it's A, that the spring force does negative work during this motion, but we also have a reasonable group that think it's C, that the spring force does positive work during this motion, and we also have a few votes for B, that it does no work. So let's have a look and see how you figure this out. So like I said, there's two ways to figure it out. One way to do it is to say, okay, I'm going to look at the direction of the force here. Okay, so for this whole motion, the force, the spring force, is going to point in the negative direction here. It is going to start at 0 and get bigger, right, the more you compress the spring, but the whole time it is pointing in a negative direction, but the displacement there of the end of the spring is in the positive direction. So given that, it seems like the work should be negative, but then you can also use the formula. So we can say, okay, we know the work by the spring is minus 1/2 k x2 squared minus x1 squared, and x2 in this case would be d, and x1 would be 0 because it started at the equilibrium length, which is x equals 0. And so we get that the work done by the spring is minus 1/2 k d squared. So in fact, both of those explanations, using the formula, looking at the vectors, tell us that the work is negative. So that's good. They're consistent with each other, right? Which is what they should be consistent with each other. So it's good to always do both if you can. If you know, like do the math and then check it with the vectors, or vice versa. Okay, so that's an example of a spring doing work. Okay, and basically whenever you compress or stretch a spring like that, it's going to do negative work because it doesn't want to stretch or compress. It wants to stay at equilibrium. Okay, now we're going to look at a new quantity. We're going to look at what's called potential energy. So if you have a conservative force, and this only works for a conservative force, but if you have a conservative force, then you can define a potential energy associated with that force, which depends on position. Okay, this only works with conservative forces. So for example, we know the gravitational force is a conservative force, so we can define a gravitational potential energy, which is equal to the mass of the object times the acceleration due to gravity g times the vertical position y of the object, where y is the vertical position relative to some point that you've defined to be y equals 0. And this is actually really important, okay, because you get to choose where y equals 0 is. And so the values of this energy, this potential energy, are going to depend on what you call y equals 0. So like, for example, if you have a problem with the cliff or something, you might define y equals 0 at the top of the cliff, or you might define y equals 0 at the bottom of the cliff. Either one is fine, but that means your values for gravitational potential energy will be different depending on which of those choices you make. So that's important to keep that in mind. And you can't switch your y equals 0 point halfway through a problem. Okay, you have to pick one and stick with it. So, for example, if we look at our object we saw in the last slide going upwards here, okay, and so instead of downwards now, well, no, we were upwards before, that's right. So, so we've got, it starts at an initial y position, has a final y position. So if we wanted to look at the gravitational potential energy here, we would say that its initial gravitational potential energy is mg y initial, and its final gravitational potential energy would be mg y final, and those are both measured to wherever we decide to set y equals 0 to be. Okay, Then we can look at, for example, the change in gravitational potential energy for this object that moves from y initial to y final, and that's just mg y final minus y initial. All right. And the other thing to notice then is we go back and we say, oh, that's interesting because that looks a lot like the formula for the work done by the gravitational force when this object moves from y initial to y final. In fact, they're opposites of each other. Okay, the change in gravitational potential energy is just minus the work done by the gravitational force. Okay, and that is actually a completely general result. You're going to see this again and again in physics, that if you have a potential energy, that the change in the potential energy is always minus the work done by the force that defines that potential energy. Okay, so the change in gravitational potential is always minus the work done by the gravitational force. And we're going to see the same thing with spring forces. And if you go on to take Physics 102 next semester, you'll see the same thing with electrical forces, because the electrostatic force is also a conservative force. Okay, so that's a really important result to keep in mind, that delta U equals minus the work for a given conservative force. Okay, so what does that tell us? Well, what if you have a scenario where the net force acting on an object is gravity? So essentially the only thing that matters is gravity. So a falling object without air resistance, okay, or another scenario where the other forces cancel out, and the only force that matters is gravity. For example, like somebody on a frictionless roller coaster, okay, where the normal force is doing no work. So in the pre-lecture videos, they had this person on a ski ramp, right? So in a scenario like that, right, if the net force acting on an object is gravity, then that means the work done by the net force is the work done by gravity. And then we know from the work kinetic energy theorem, right, the work energy theorem, that means that the work done by gravity must equal the change in kinetic energy. All right. So remember, this is only if the net force acting on an object is the gravitational force. So, for example, if we go look at a falling object now, okay, that starts at y initial and ends up at y final, like this, okay, we know that the change in gravitational potential is minus the work done by gravity, right? And work done by gravity must be equal to the change in the kinetic energy. And so you get that the change in gravitational potential energy is equal to minus the change in the kinetic energy. And that's probably something you've seen before, okay? And that's a useful result if you're looking at falling objects. It's just important to realize it only works for falling objects and other similar scenarios where the net force on an object is gravity. It doesn't work if there's air resistance or friction or other things going on. It doesn't work if there's a drive force, for example. So for a falling object, what does this mean? This means the work done by gravity is positive, the change in the gravitational potential energy is negative, and the change in kinetic energy is positive. And that's exactly what we know happens, right? For a falling object, right? It speeds up, okay? Its kinetic energy increases, okay? In a way, you can think of the gravitational potential energy being converted to kinetic energy. That's kind of a useful way to think about it sometime. And what's going on here is that gravity is doing positive work on a falling object. You can see that the displacement and the force point in the same direction. But again, if something is rising, all right, then you get the opposite effect, right? Now gravity is doing negative work. Now the change in gravitational potential energy is positive, and the change in kinetic energy would be negative. So this is like when you throw an object up into the air, when it's rising, it's gaining in gravitational potential, it's slowing down, its kinetic energy is decreasing. And that's because gravity is doing negative work. Okay, remember, if you do negative work, you're causing an object to slow down. All right, so like I said, one way to think about this is that your potential energy is converting into kinetic energy, okay, on the way down, and then on the way back up, it's vice versa. in a way your kinetic energy is converting into potential energy. Okay, so potential energy, kinetic energy are another way to look at the scenario, or you can look at it in terms of work done by gravity and kinetic energy. They're sort of two parallel different ways to look at the same situation, okay, that are related to each other. So any questions on that so far? Okay, so let's try another poll question now on this. I think we're going to do this one quickly because I think this one's relatively straightforward. So we've got 4 choices here. Okay, so what do we have? We have 2 balls, one that has twice the mass of the other, and they're released from the same height. And just before hitting the ground, the kinetic energies are K1 and K2 respectively. And the question is, how do K1 and K2 compare? How does the kinetic energy of the mass m compare to the kinetic energy of the mass 2m? Oh, I just realized there's a typo in that first one. That first one should be K1 equals 2K2. Here, I can fix that. See if I can fix that real quick. I think of that too. There we go. Sorry about that. Okay, let's do 10 more seconds on this one. So go ahead and guess if you're not sure. Okay, 5, 4, 3, 2, 1. We've still got a few guesses coming in. All right, let's have a look. So what do we have? So the biggest group is going for C. We've got 83 out of about almost 200 are going for C. And then we have sort of a tie between A and B. So C says that K2 equals 2K1. B says that the 2Ks are equal. And A says that the kinetic energy, the smaller mass, is twice the kinetic energy of the bigger one. All right, so let's have a look and see how you would figure this out. All right, so how would you figure this out? So let's start with putting in a y-axis, and I'm going to label the starting position H, and the final position will be 0. Okay, so my origin will be at the ground. Okay, so we know that the change in gravitational potential energy is minus the change in kinetic here, because the only force acting is the force due to gravity. Okay, So let's look at the first mass. So I wrote this out in all its gory detail. So you can see all the steps here. Normally I won't write all of these steps down, but I thought just once I would do that. So what do we get? Changing gravitational potential energy is mg y final minus y initial. In this case, y final is 0, y initial is h. So we get the change in gravitational potential energy is minus mgh. That's got to be equal to minus delta k. And what's delta k? Minus delta k, sorry, is minus the final kinetic energy minus the initial, which is 0. And so ultimately you end up with that the kinetic energy of mass 1, okay, is mgh. And then you do the same thing for the second mass, for 2m. You go through the same calculation, only plugging 2m in everywhere, okay, because that's the only thing that's different is the mass. And you end up with the kinetic energy of mass 2, of 2m, is 2mgh. And so you end up with the second mass, 2m, having twice the kinetic energy of the first one. Okay? So our answer is in fact C. So well done for the biggest group there. I mean, if you think about it, remember we talked about how the acceleration of these two objects would be the same. And if the acceleration is the same and they both start from the same height at rest, like this, then they're both going to have the same velocity, right? Just before they hit the ground. The only difference is that one of them has twice the mass. So the same velocity, remember we saw the kinetic energy is 1/2 mv squared, okay? So if they have the same velocity, it's just the mass that tells you that basically the difference in the kinetic energy there. Good. Okay, so you can see how that works. So now let's do a similar one. This one's slightly different and requires a little bit more thought. So let's set this one up. We've got 4 choices again. So what do we have for this one? So this one says, so now we have a block of mass m, and it's launched up a frictionless ramp with an initial speed v, and it reaches a maximum vertical height h. A second block, having twice the mass, 2m, is launched up the same ramp with the same initial speed. What is the maximum vertical height reached by the second block? So remember, we have a frictionless ramp here, okay? So in some ways, this is similar to the last scenario of the falling object, except our object's going up instead of down. And you can see it starts with a certain amount of kinetic energy, and as it rises, it's going to slow down, right? So you have to think about where that kinetic energy is going. And there's no friction here, so we're not going to lose any of it to friction. It's not going to be converted to heat in friction by the block rubbing against the surface. Okay, I think we'll do 10 more seconds on this one. So go ahead and guess if you're not sure. Yeah, we need Jeopardy music here. You won't lose any money by guessing here. Question. No question? No? Okay. 5, 4, 3, 2, 1. So on this one, there's a bit more indecision. Okay, it's almost a three-way tie, but not quite. So the slightly largest group is going for A, but there's a reasonable sized group going for B. And we've got also a reasonable sized group going for C. So the choice is between H, square root of 2 times H, and 2 times height. All right, so I'm going to do this one a little bit quicker than I did the last one. Okay, so let's end the poll there. So what do we know? What do we know? We know that in this case, it's also true that the change in gravitational potential energy is equal to minus the change in kinetic. Because if you think about what's going on here, the only forces acting on our mass are the force due to gravity and the normal force. Okay? And the normal force does no work because it's perpendicular to the displacement of the mass as it goes up the plane. So the only force doing work is our conservative gravitational force. So it's definitely true that delta U grav equals minus delta K here, just like it was for our falling object in the last question. Okay, and so what does that mean? That means that what's the change in gravitational potential? Well, that's just mgh, right? So it's just the final gravitational potential, mgh minus 0. If you set, and usually we're going to, set our 0 point to be our starting point for our gravitational potential energy. Okay, and then similarly, right, we're looking at it reaching its maximum vertical height, which means it's going to start with some speed v and end up with speed 0. So its change in kinetic energy, right, is minus 1/2 mv squared. It loses all its kinetic energy, and so minus delta k is just plus 1/2 mv squared, right? And what does that tell you? It tells you that the final height for our object is just 1/2g v squared. And what do we notice right away? That it doesn't depend on the mass of the object, that the mass cancels out here. Okay, so how high your object's going to go if it starts at velocity v, okay, isn't going to depend on the mass. Okay, and so in fact, the answer is A here. Okay, if you had a second blocks with twice the mass and you launched it with the same speed, it would go to the same height. Okay, so questions? When does the mass matter? Well, the mass would matter if you had friction, right? Because then that would affect the normal force. Okay. Yeah, exactly. So it depends on, you have to look at each scenario separately. But in the case of things dealing with gravity, because the acceleration due to gravity doesn't depend on mass, it's often the case that mass doesn't matter. Okay, but you do have to look at each scenario and analyze for yourself whether the mass is going to cancel out or not. Okay, other questions on that one? Okay, so the negative sign went away because the change in kinetic energy was negative. So the change in kinetic energy is the final kinetic energy, which is 0, minus the initial kinetic energy, which is 1/2 mv squared. So it basically canceled out. All right, so let's talk about spring potential energy now. So this is the other potential energy. So you can, just like with gravitational systems, because the spring force is conservative, you can define a spring potential energy, which basically depends on how much the spring is stretched beyond its equilibrium position. So we say that the potential energy of a spring is equal to 1/2 k, which is called the spring constant, times the amount of stretch, x squared, of the end of the spring. Remember, this is based on defining the unstretched, uncompressed position as x equals 0. So this depends on that definition. And so then you can see, if you look at the change in spring potential energy here, for example, when you're at the end of your spring, like in our picture, goes from x1 to x2, then the change in spring potential would be 1/2 k, the final position, x2 squared minus x1 squared. And we can see right away, we know that that's equal to minus the work done by the spring, right? Because we've seen that formula before with a minus sign in front of it for work done by the spring. And so again, we see that the change in potential energy is equal to minus the work done by, in this case, the spring force. All right, so just like we saw with gravity, delta U equals minus work, right? That always, always happens for conservative forces. So now, if your net force is the spring force, so like if you had a mass on a horizontal surface, where the normal force and the weight were not doing any work because the surface was horizontal and the mass was moving back and forth, okay, then the net work would be the work done by the spring force, and then the work done by the spring force would equal the change in kinetic energy of the object. Okay, so much like we saw before with the gravitational force, so if the final stretch or compression, okay, this works for both stretching and compressing, because with those squares in there, it doesn't matter if your x's are positive or negative, you'll still get the same difference here in potential energy. So if the total stretch or compression x2 squared is greater than x1 squared, then the spring is doing negative work because the spring doesn't want you to stretch or compress it, right? That means what's happening is that you're storing, by stretching a spring, you're actually storing energy in the spring, sorry. So your change in spring potential energy is going to increase. It's going to be a positive. And that means that the change in kinetic energy will be negative. Okay, so you can imagine an object on a mass on a spring going back and forth, right? And you probably have seen what happens. It's fastest at x equals 0. It slows down as it stretches. Okay, so as this potential gets bigger, the kinetic energy gets smaller until it comes to a maximum point where it has maximum spring potential energy and no kinetic energy, and then it turns around and goes back the other way. It has its maximum velocity at the equilibrium position, and then it slows down going the other way until it's got its maximum compression. And again, it'll have maximal spring potential energy and no kinetic energy. And we'll look at this in a minute with one of our FETs. And then likewise, going the other way, if you uncompress or unstretch a spring, then the spring's doing positive work, the change in the spring potential is negative, and the object will speed up again, and its change in kinetic will be positive. All right, so let's try a poll question on that. Let's see how it works. This one's got 5 choices. So I'm going to put them all in here. Okay, so what do we have? So we have a block attached to a spring, and it's oscillating between point A, fully compressed, and point B, fully stretched, on a frictionless table. Okay, and assume that those are equal distant here. Okay, so 0 to B is delta X, and 0 to A is also delta X. They're both delta X. Okay, the spring is unstretched at point 0. And the question is, what is the change in potential energy? So this is the spring potential energy when the block moves from B, fully stretched, to A, fully compressed. And I just noticed another typo. This is what happens when I do things late at night. There should be a K and D there. So it should be minus 2K delta X squared. I left my K out. See if I can, I'm going to fix that one really quick. Let's put a K in there. There we go. So remember that the spring potential energy is 1/2 kx squared, where x is how far you're stretched from x equals 0, or how far you're compressed from x equals 0. Okay, I think we're going to do 10 more seconds here. So go ahead and guess if you're not sure. More Jeopardy music. Okay, 5, 4, 3, 2, 1. Let's see what everybody thought. Looks like this one was a little bit trickier. Springs are a little bit trickier than gravity. Gravity we have a bit more experience with, right? Okay, so what do we got? We have the largest group are going for D, minus 2K delta X squared. The next biggest group, almost a tie, is C, that the change of potential energy is going to be 0. And then we also have a reasonable group going for A, which is it's going to be positive 2K delta X squared. All right, so how does this work? So what are we going to do? So let's have a look. So what is the change in the spring potential energy? So remember, the formula was 1/2 K, the final x position squared minus the initial x position squared. Okay, and so it's minus 1/2. So final position at A is minus delta x, and that quantity will be squared. And the initial x position, x1, was delta x. Okay, remember I said it was symmetric here. If a spring oscillates symmetrically about its equilibrium position. And so basically, because of the squares there, the change in potential energy here is actually 0. Okay, so in fact, C was the right answer. Okay, so this is where you have to be careful because of the squares. Okay, so you have just as much potential energy in a spring when it's compressed by delta x as when it's stretched by delta x. Okay, you get the same amount of energy, so that means the change between those 2 points is 0. Okay, it has the same amount at either of those two extremes. Questions on that? So you can see why this stuff is a little bit tricky, and it's good to just kind of think about it for a while. So the last thing we're going to look at today is to kind of put everything together and talk about a quantity we call total mechanical energy, which can be quite useful if even if there are non-conservative forces. But the idea is that you can define this total energy, total mechanical energy, which is the sum of the potential energy and the kinetic energy of an object. Okay, so that means there typically can be up to 2 different types of potential energy. So it would be the sum of the gravitational potential energy plus the spring potential energy plus the kinetic energy of the object. And then if only conservative forces are acting, then you can show that this is a conserved quantity. And what do we mean by conserved? That means that it doesn't change, okay? That delta E mech will be 0 for any process, okay, any type of motion, if only conservative forces. So if the only forces acting are the spring force and gravity, then this total U plus K is not going to change. And you can actually prove that to yourself by calculating, well, what is the change in mechanical energy? So it's final minus initial. We know that that's equal to the sum of U plus K. And so if you go through, you can see that delta E mechanical, not surprisingly, is just equal to the change in potential energy plus the change in kinetic, right? If the total thing changes, it's got to be equal to the sum of the 2 individual changes, okay? And we know that that has to be equal to 0 because we saw earlier that change in potential energy must equal minus the change in kinetic if only conservative forces are acting. So if delta U is always opposite delta K, if delta U goes up as much as delta K goes down, then the sum of those two is always going to be 0. Okay? So as they said in your pre-lecture, the upshot of this is if only conservative forces do work on the object, the sum will be 0. Okay, the sum of the change of the potential energy and the change in kinetic energy will always add up to 0. Okay, the total mechanical energy can transform between kinetic and potential forms. It can be all potential, all kinetic, or some combination of the two, but there will never be a net change. And we can use this fact to solve problems. Okay, so we can look at the total mechanical energy and say that the amount you had before in a problem equals the amount you had after. Okay, and that's one way to solve a problem. Or you can look at the change in potential energy and the change in kinetic energy and then know that those two things have to add up to 0. So there's always more than one way to do these energy problems. And so depending on which way you want to do it, you should still get the same answer. They're all valid methods, right? And so that's a good way to check your work. All right, so I had one more question for you, but we've run out of time, so I'm going to save that one. So I'm going to show you, I wanted to show you what springs look like when they're vertical. Because when springs are vertical, then you have to deal with both types of potential energy. So I think we'll start next time with that, and we'll stop here. So if anyone has any questions, I'm happy to answer them. but I'm going to stop our recording now.